This screencast is going to go over a phase diagram for a ternary system. In the following example, we have a stream that's 50% mass acetone and 50% by mass water. And this is mixed with a pure stream of methyl isobutyl ketone. The mass feed rate of the acetone water stream is half that of the MIBK stream. We're asked to determine what the outlet mass of the water-rich phase is per mass of water in the feed. So with any material balance, the first place we should start with is a diagram. So here's my diagram where we have two feed streams, one which is 50% by mass acetone and 50% by mass water, as well as a second stream that is 100% MIBK. Now these are mixed in a tank, and then they equilibrate and separate into two streams, a water-rich phase and an MIBK-rich phase. And you can see I've written out the three unknown compositions since each phase will contain parts of each of those species. And the only other information that we're given that we should write here is that the mass feed rate of the acetone water stream, so M1, is half that of the MIBK stream. So this is can be confusing the way to write this, but just double check it. Basically, we're saying that the MIBK stream is twice the first stream. So if that makes sense, now we could write it the same way where M1 would have equaled half M2. And I just rewrote it so it's 2M1 equals M2. And the last thing to do with any diagram, if it hasn't been given, is to choose a basis. And we're going to go ahead and pick 1 gram per second of acetone in the feed stream. It just keeps it simple that way. Since the question was asking for the amount of water per mass of water, I could have written it that way too, but because it's 50-50 stream, it's easy to see that you have 1 gram per second of acetone and 1 gram per second of water, and that's in M1. So that's all the information that we've been given. Now we go basically write our material balances. So our material balance for the total is M1 plus M2, and that's going to be what goes into the system. And basically what comes out of the system has to also be the total mass, and we've written it as MW and M. So you have N equals out. So in this case, M1 plus M2 equals MW plus MM. Now we've been given a relationship for M2 to M1. So we'll go ahead and rewrite that. And if you recall, M2 equaled 2M1. So we have 3M1 equals MW plus MM. And that's our total balance. Now we can write an acetone or a water or an MIBK balance. So I'll go ahead and write a water balance since that's kind of what we're interested in here. So we know that 50% of stream 1 is water, and that's going into the system. And that has to equal some mass fraction for the water-rich phase and some mass fraction in the MIBK-rich phase. So we'll go ahead and put the unknown times MW plus some unknown times the mass flow rate in the MIBK-rich phase. So we first need to find where we lie on this diagram going into the mixer. So if we use the basis of 1 gram per second of water and 1 gram per second of acetone, then we know there must be 4 grams per second of MIBK based on that relationship of 2 to 1. So if we do this, we need to determine the mass fractions of each. As you can see, the total is going to be 6 grams. So 1 gram and 6 grams is going to give us 0.167, 0.167, and 0.667. So I'll round up a little bit on this diagram since we're reading it on a chart anyways, and follow you through this. So let's use a highlighter here. We're going for a mass fraction of around 17% acetone. We're going up the chart, so it's going to be between the 15 and the 20, so somewhere in there. For the water, we're going to the left corner. So we start on the right side, and it's going to be somewhere between the 15 and 20, so somewhere in here. And then 67% is going to be somewhere between 65 and 70, which puts us somewhere right in here. That should read 60. So at this point, you can see we're in the envelope, so we are going to get phase separation. We're going to go ahead and draw our tie line. So if we follow over to the right side, should be right there, and if we follow down into the left side, looks like it's about halfway between those two tie lines. Cell draw right there. So now we have our MIBK rich phase and our water rich phase, so we can start filling those in. Since we're doing our water balance, that's what we're interested in. So our water percentage looks like it's between 85 and 90, so we'll go ahead and say it's 87. So this is going to be 0.87. And in our MIBK phase, water looks like it's just less than 5, so we'll say it's 4. Okay? So those don't have to add up to 1. Remember that. They're just the fractions in the two streams of water. Okay? So now we have our balance there and our balance for the total. It looks like we have 3 unknowns and 2 equations, but we do have a basis for M1. We know it's 2 grams per second. So we'll fill that in for M1. We have 2 equations, 2 unknowns. So we could go ahead and solve this. So you can see I've simplified the water balance to get 1 equals 0.87 MW plus 0.04 MM. And the total simplifies to MW equals 6 minus MM. So we plug the second equation into the first, and I'll do that on the original page. So you can see at the top right corner I've rewritten the balance and simplified down to solve for the mass flow rate of both MIBK and water. I got 5.08 grams per second of the MIBK rich phase and 0.92 grams per second of the water rich phase. You have to ask yourself if this kind of makes sense, and recall that we did have 4 grams per second of MIBK coming in, and based on the equilibrium of the tie line, we have very little MIBK in the water rich phase. So majority of the MIBK is going to be in that MIBK phase, and we're taking some of the acetone and water with it, so it should be higher. You could double check those answers. But the question asked, what is the outlet mass of the water rich phase per mass of water in the feed? Since we used the mass of water in the feed as a basis of 1, we're just going to say that it is 0.92 over 1. So I'll just highlight this answer since that's what we're looking for. So hopefully this gives you an idea of using a ternary phase diagram in conjunction with a material balance in solving what the equilibrium concentrations are going to be in the 2 phases, if there are 2 phases.